Hi, welcome to the Olympiad geometry. Let's continue our study. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. So we're going to talk about XMO. It's also a problem from audience. Thanks for the feedback from the audience. This is a problem of Bmo National Selection Test Nst4 2015, problem 1. This is a very interesting problem, and I want to make a point from this problem. Basically, this point I already repeated like many times, but I think this problem is a very good example to make this point. The point is that sometimes when we try to solve a difficult problem, we know that we have to find some auxiliary lines, but we just don't know how to make the auxiliary lines can help us, right? The idea is that we can think of how to draw the figure with using ruler and compass only. Why this is important? Because when you think of just drawing the figure that satisfies the problem set, you have to draw lots of perpendicular lines or parallel lines or circles, right? And all of these lines and circles can be your auxiliary lines. Okay, that's a point. So for this problem, let's look at it. In trapezoid ABCD, the sum of the length of the base AB and CD is equal to the length of the diagonal BD. So it's a specific trapezoid. Let M be the midpoint of BC and E the reflection of C in line DM. Prove that two angles are equal. Okay, the first thing is that we know it's a problem about a trapezoid. So let's call it ABCD here. And the property is that AB plus CD equals to BD. Right, that's our property. Then you can think of how can we draw a trapezoid satisfy this problem set. The answer is that if we just draw a straight line here and we find point B here, and we can draw a circle that's centered at B with arbitrary radius, right? And we know that this can be our diagonal BD, which means from B to here, let's call it D prime. BD prime would be the base summation that AB plus CD, right? Which means if I just pick a point, call it as A, then if I connect D and D prime, and I draw a parallel line to BA that passing through point D, and then I can just draw a parallel line to DD prime and passing through A. This intersection point should be point C, right? Now we have our trapezoid here. We have A, B, C, D here, and we know that CD equals to AD prime. It makes that BA plus CD to be BA plus AD prime equals to BD. So we know that BADC is our trapezoid, and we know, so if we just think about the ABCD trapezoid here, and how can we find this D prime? We just need to draw a parallel line to AC that passing through D, right? And extend the BA to meet this parallel line on the point D prime, and the D prime is a point we're looking for. Okay, so now we have BD prime equals to AB plus CD. And we know because CD is in parallel with BA and CA is in parallel with DD prime. That makes AD prime DC to be a parallelogram. And this is extremely important. I'll explain it later. And for the rest part of the problem set, that we know M should be the midpoint of the segment BC here, and E is a reflection of C in line DM. So we connect the DM here, and we find the reflection of the C to DM. Now we connect this one here. This point is E, right? And we want to prove that angle AEB. Let's connect AE, connect BE. We want to prove that angle AEB equals to angle ACD. Okay. So M is a midpoint. And we want to prove angle AEB equals to angle ACD. So we know that we're very far away from our target. Just look at the figure and try to find try to find some conclusions here as much as possible. We already find that AD prime DC is a parallelogram, and we know that this angle, the angle AD prime D equals to angle ACD, right? This angle equals to this angle. This one equals to this one. And remember that, how can we find the D prime? We have the conclusion that BD equals to BD prime, right? So we easily have the result that angle BD prime D equals to angle BD D prime, right? So this angle equals to this angle. That just remind us that if we call this point the point that is this point is the intersection point of BD and CA, let's call it as F, right? Then we know that the trapezoid FAD prime D, in this trapezoid FAD prime D, because the base angle are equal, right? The angle AD prime D equals to angle FD prime. That means FD equals to AD prime. So for here, we got lots of segment to be equal, right? CD equals to AD prime and equals to FD. So CD equals to FD, which means triangle CDF is an isosceles triangle. Isosceles triangle, right? So this angle equals to this one. And we know that angle CFD equals to angle BFE. And we want to actually prove that angle BEA equals to angle ACD, which means we want to prove angle BEA equals to angle BFA. right? Because angle ACD equals to angle CFD equals to angle BFA. So basically we want to prove this, which means we just need to prove that BAEF are cyclic. Right, we just need to prove this. Now let's connect FE. Okay, let's connect FE here. And think about the problem set what we haven't used yet. That M is a midpoint, right? M is a midpoint means that MC equals to MB. And we know that E is a reflection of C to MD, which means MC equals to ME, which means the triangle CEB is a right triangle, right? The angle CEB is 90 degrees. So CE is perpendicular to BE. And because E is a reflection point of C to MD, so CE is perpendicular to MD, right? So CE is perpendicular to BE and CE is perpendicular to MD, which means MD is in parallel with BE. And this reminds us another auxiliary line that because M is a midpoint of CB, and we know that MD is in parallel with BE. So if we extend BE, meet the extension of the CD on another point K, then we know that D must be the midpoint of CK, right? So in that case, CD equals to DK. And extend it, because we already know that CD equals to DK equals to AD prime equals to FD, so it equals to FD, which means DC equals to DK equals to DE, right? Equals to DE because E is a refraction of C to MD, right? So DC equals to DE equals to DK, and also it equals to DF. Right, that's all we have. Then we know that C, F, E, K, these 4 points are cyclic. Right, these 4 points are cyclic. C, F, E, K, these 4 points are cyclic because D is the center, right? DC equals to DF equals to DE equals to DK. So what we can get from here, these 4 points are cyclic. That means the angle FEB equals to the angle FEB here, this one, equals to angle, this angle equals to angle ACK, right? This one. Equals to this one. The angle FEB equals to angle ACK. FEB, this one, equals to angle ACK, equals to this one. And because CD is in parallel with BA, so we know that the angle ACK is actually angle ACD, right? And it equals to angle CAB. So we know that angle FEB equals to angle ACD equals to angle BAC, which means the angle FEB equals to angle FAB, which means FBAE are cyclic. Right? So we get that FBAE are cyclic. When FBAE are cyclic, it's certainly that the angle BFA equals to angle BEA, right? The angle BFA equals to angle BEA equals to this one. And then we know that because angle BFA equals to angle ACD, so the angle BEA equals to angle ACD. We finish our proof. So as you can see, that the only use of CD plus BA equals to BD is to construct this parallelogram. And when we have this parallelogram, it's critical because based on this parallelogram, we find that in the trapezoid AD prime DF, AD prime equals to FD. And based on that AD prime equals to FD, we have the conclusion that CFEK are cyclic. And based on that, we do the angle chase. We can find that the angle FEB equals to this angle and equals to this one. Eventually, we prove that FBAE are cyclic as well, right? And then it's easy to show that angle BEA equals to angle BFA equals to angle ACD. Okay, that's for this problem. It's an interesting one. I hope you like this video. See you in next one. Thank you.